Here in section 5.6, we finally have enough information that we can actually solve equations that contain exponentials, and actually those that contain logarithms as well. So we're going to look at equations that contain both logarithm and exponentials. First of all, remember that in general, when we solve equations, our basic goal is to apply inverses in order to undo what's been done. We're going to see this repeatedly in this section, and it's going to be very important to keep in mind our two inverse functions that we've been working with, right? Our exponential functions and our logarithm functions. Are inverses of one another. They do and undo, so I can kind of get rid of one by applying the other. All right, we're actually going to start by solving equations that contain logarithms. Basically, the idea is we want to isolate the logarithm, that is, get it by itself on one side of our equation. And then in order to get rid of the logarithm, we're going to apply the exponential function. That's the inverse. That'll get rid of the log, and it'll give us an equation that we can solve for x. Keep in mind, as always, when you're solving an equation, be sure to always do the same thing to both sides. And in this case, with our final answer, we also need to remind ourselves that we got to make sure we're in the domain of the logs in the equation, right? A reminder, the domain of log functions is only positive values, right? The argument has to be positive or greater than 0. All right, let's try this out. In this first one, we would like to solve our equations. Only going to worry about real valued solutions here. And I already have my logarithm all by itself over here. So I'm going to jump right to step 2. I'm going to apply the exponential function that is the inverse. Well, the inverse of a log base 5 is an exponential base 5. So I'm going to say exponential base 5 on the left side, exponential base 5 on the right side. I put a base 5 on both sides, and my original values are now in the exponents. All right, that's the composition of an exponential and a log. Because those are inverse functions, we end up with just x on the left-hand side. And 5 cubed, of course, is 125. I didn't say it outright, but I probably should have. 125 is just fine. 125 is certainly a positive value to put into that argument, so it fits the domain. All right, let's try another one. In B, my logarithm is not yet isolated. My goal is to get the logarithm by itself. And my logarithm here is the logarithm base 3 of x squared. Can't split that apart, that's all together. In order to isolate it, I'm going to have to add 5. And then I need to divide by the 4. All right, I've got a log base 3 here that I would really like to get rid of. So I'm going to say, what's the inverse of the log base 3? It's the exponential base 3. So exponential base 3 on the left. And then I must also do the same thing, exponential base 3 on the right. Inverse functions, which leaves me x squared equals 3 to the 4th power, or 81. And to solve for x, I'll take the square root of both sides. Keeping in mind I need to use the plus or minus when I do that square root method. So x ends up being plus or minus 9. Now I always have to check, are these both valid? In this case, notice that in the original equation, I had x squared in the argument. So it really doesn't matter if it's a positive 9 or a negative 9. When I square it, it's going to give me an 81 in here, and 81 is certainly within the domain of the log function. So these are both good answers. Right? Not every negative number doesn't work. You just want to be cautious of them. All right, I have a few more problems for us to try here with our log equations. In C, looks like the logarithm is already isolated. Remember, this is the logarithm of 6x minus 2, right? That 6x minus 2 is not a multiplier. It's the argument, or the inside, of the logarithm function. That's a common log, since the log wasn't, or the base wasn't written. If I want to, I could rewrite it with a base of 10. And to get rid of a log base 10, I use the inverse function, an exponential function with a base of 10. And on the right again, an exponential base 10. Exponential and the log base 10 are inverse functions. So the left-hand side becomes 6x minus 2 equals 10 to the first is still going to be 10. If I add the 2, 6x is 12, and dividing by the 6 gives me x equals 2. If x is 2, that would be 12 minus 2, 10 inside that log. Positive value, so no problem. I'm within the domain. All right, notice in D how the placement of the parentheses changes this into a completely different problem. Right? The log of 6x is the log term, and I'm going to isolate it. So I'm going to add 2 to both sides. I can do that since the 2 is not in the parentheses. It's not part of the log function. So I have the log of 6x equals 4. Again, if you want to, you can put that little base 10 there as a reminder. Common logs are logs base 10. All right, inverse of a log base 10 is an exponential base 10. Exponential base 10 on both sides. Inverse functions there. So I get 6x equals 10,000. If I divide both sides by 6, I can get a decimal approximation. The lowest term's fraction would just be 5,000 over 3. But if I want to, I could also get a decimal approximation. It's about 1666.67. All right, this next problem is a little bit different. Notice that this time the unknown, the variable, is in the base. So I'm solving for an unknown base. Despite the fact that the unknown is in a different position, I'm actually going to work on this problem exactly the same way. I'm going to isolate the exponential. Notice this time the exponential is the log base b of 45. So I would add the 1. And then I would divide by the 3. All right, to get rid of the log base b, I use an exponential base b. It's the inverse function. Inverses. And so the left-hand side just becomes 45, and the right-hand side is b cubed. If I want to get rid of that exponent of 3 to solve for the b, I can use the reciprocal exponent, the 1/3 power. And of course, if I do that on one side, I have to do that same power on the other side. That's just going to give me b to the first. And 45 to the 1/3. Oops. Got another calculator here. When it doesn't go into the exponent automatically, I got to supply some parentheses there. 45 to the 1/3 is about 3.557. Approximately 3.557. All right, F. Let's see. The log term is this whole thing, right? Log base 2 of x squared minus 6x. So to isolate that, I would have to subtract the 5. All right, get rid of a log base 2 with its inverse, an exponential base 2. Exponential base 2 on the left, so I also do exponential base 2 on the right. Those inverse functions out of there. And I have x squared minus 6x is 2 to the 4th, or 16. Let's see. That's quadratic. And to solve a quadratic equation, I'd like it to be equal to 0. So let's subtract the 16 to get 0 on the right-hand side. 3 terms, so I can go with sum and product. I am looking for a sum of -6 and a product of -16. So I'm thinking -8 and 2 here. And since that's just a 1x squared, I can use sort of the shorter version. I know how to split that up as x times x, and then -8 and +2. So I either have x minus 8 equals 0, or I have x plus 2 equals 0, and x equals 8, or x equals -2. I've been getting positive answers, so I haven't worried too much, but I probably should check that -2 and make sure that it's going to be okay. What I'm going to do is I'm just going to plug the -2 into the x squared minus 6x to make sure that's positive. And indeed, that makes that a positive 16. So x equals -2 is just fine. All right, my last 2 examples of log equations are going to touch on the natural log, that log base e. So when I have a natural log equation, the inverse function for the natural log is going to be the exponential base e. So exponential base e on the left equals exponential base e on the right. Because that is a log base e, those are inverses. And the left-hand side's just 4x plus 7. Now what you do next kind of depends on what you're asked for. If you're asked for an exact answer, e to the 5th, of course, will never come out evenly. E itself is not a decimal that ever ends. So if I want to keep this exact, I'm going to have to leave the e to the 5th in the answer. If I do this, it's going to look like, see, subtract the 7, and then divide both sides by the 4. And if I want an exact answer, that's the best I can do. As soon as I try to evaluate e to the 5th, it becomes an approximate decimal. Now, if I do want a decimal approximation, let's say to 3 decimal places, then of course either Desmos or your calculator will do this just fine. In fact, I've been using the calculator a lot. Let me do this one on Desmos. E to the 5th minus 7 over 4. There we go. It is about 35.35. I said 3 decimal places. 35.353. And you'll note certainly the Desmos understands what E is. No problems there. All right, let's go back to, oops. There we go. Hang on one second. There we go. Back to my problem. Again, there was the exact answer. There was the decimal approximation. All right, last log equation. It's got a natural log again, but this time the natural log is not isolated. So I need to isolate, or in other words, get that natural log of 5x by itself. Again, can't emphasize enough, that's not natural log times anything, it's the natural log of something. 5x is the argument. So to get that by itself, I'm going to add the 3. And then divide by the 2. Once again, although I won't write it that way, I know in my mind that the natural log is a log base e. So the inverse function is the exponential base e. And I have to do that exponential base e on both sides. Get rid of those inverse functions. And what I'm left with is 5x equals e squared. If I want an exact answer, it's just going to be e squared divided by 5. If I want a decimal approximation, see e squared divided by 5 is approximately 1.478. All right, so that's solving log equations. Isolate the log and then apply the inverse function, whatever exponential function is your inverse, to basically get rid of the log in your equation. When we want to start solving exponential equations, we're going to continue to use the inverses. So once again, we're going to start by isolating, this time isolating the exponential. And then now to get rid of the exponential, I'm going to apply the logarithm function. That is its inverse. And then that should get me something I can solve for x. Again, never forget, got to always do the same thing to both sides, right? Now, as part of this process, we are going to occasionally need to evaluate logarithms that don't come out evenly. We know the calculator has a button for that if it happens to be a log base 10 or a natural log. But what if I've got some other base? There's a way to do that on both the calculator and Desmos, and I'm going to show you both of them so that we have that kind of in our toolbox before we start solving our equations. Let's start with one that we know the answer to. The log base 2 of 8. I know that 2 to the 3rd power gives me 8, so that has to be 3. Let's check that out and see if we can get that same answer on both the calculator and Desmos. If you're working with a graphing calculator like the TI-84, in the Math menu, right here, if you just scroll down far enough, hang on. I've got an older model. Let me see if I've got a newer one here. This wasn't on the old models. Math menu, scroll down. There it is. Eventually, hopefully, if your calculator is newer than that other one, you should come to log base. And when I do that, I get a little template, and I can say exactly what I want. I want log base 2 of 8. And we do get that 3 just like we expected. I'm going to do one more and then we'll pop over to Desmos and do them both on Desmos as well. So yes, we did get what we expected, right? All right, what about the log base 6 of 82? Notice this time there's no nice whole number power of 6. That's going to give me 82. I know 6 squared is 36. 6 cubed is 216. And 82 is somewhere in between there. So all I really know is that my answer should be between 2 and 3 somewhere. Other than that, I can't give an exact value. So let's use that log base button again. We go to our Math menu, scroll down, select the log base, and this time I want the log base 6 of 82. It's about 2.459. And again, notice it was between 2 and 3, just like we expected, so I can say yes, that answer does make sense. Okay, I'm going to go over to Desmos and we're going to redo both of those examples using a Desmos template. So what you're going to want to do is down here in this little show keypad area, if you click on that and come on over here to the right, there's this button called Functions. If you look around just a little bit, well, let's see. We should find our log base. Did I miss it? There it is, sorry. Log base A, that's what I want. So it's going to click on that, and I wanted the log base 2 of 8. We know this one should be 3, and there it is, 3 itself. Let's try that second one, the log base 6 of 82. Again, it's in the functions. Look around a little bit. I think it was under calculus. Don't know why, but it is. There it is, log base A. This time it's a log base 6 of 82. And that gives us again about the 2.459. So either a calculator or Desmos will calculate logs of any base. All right. So let's apply that now as we solve a few exponential equations. See, we're going to go ahead and give both an exact answer and then also one rounded to 3 decimal places. So if I have 8 to the x equals 100, I definitely have my exponential isolated. So I'm going to say, what's the inverse function for this exponential base 8? Well, the inverse would be a log base 8. So I'm going to take the log base 8 of 8 to the x. And then I also have to take a log base 8 of 100 on the other side. There are those inverse functions again. That's the composition of the logarithm and the exponential. So that just gives me x. And the exact answer is the log base 8 of 100. Now I can turn that into a decimal approximation by going down to that log base option and doing the log base 8 of 100 that way. Extra parenthesis there, there we go. Oh my goodness, I got an extra 0 and everything. Let me try that one more time. Go down to that log base, and it's the log base 8 of 100. There we go. About 2.215. And again, you could do the same thing on Desmos. All right, let's try B. I need to isolate my exponential, and only that 5 to the x power is the exponential. So I want to get rid of everything else. We'll start by adding the 4. And then I can divide by the 3. So I get 5 to the x power equals 9. All right, exponential is isolated. So now I'm ready to apply the inverse. The inverse of the exponential base 5 would be the log base 5. And if I took the log base 5 on the left, I better also take the log base 5 on the right. All right, there's our inverse functions, leaving us just x. And that is the exact answer. If I want to turn that into a decimal approximation, that would be the log base 5 of 9. That's about 1.365. All right, I got a couple more here. In C, the exponential function is already isolated, right? That whole 2x minus 5 is all up there in the power. So I want to get rid of the exponential base 4, and to do that I need a logarithm base 4. So I'm going to start right out with the log base 4 on both sides. All right. Inverse functions, I can get rid of those. So I have the log base 4 of 15 equals 2x minus 5. If I want to stay exact, I have to leave that logarithm written out like that. I can't evaluate it and get an approximation, at least not quite yet. So to solve for x, let's add the 5. Log base 4 of 15 plus 5 equals 2x. By the way, notice again, that 15 is in the argument of the log function. I cannot combine that with the 5 because that's kind of stuck inside that log function until I do something to get rid of it. All right, finally, to get x by itself, we'll divide by 2. So that would be my exact answer, and that's about as good as it gets, unfortunately. We can, however, get a decimal approximation for that. And let's see, I'm going to go ahead and use Desmos for this one. I want the log base 4 of 15. So over to functions. There it is, log base 4 of 15. And then I want to add 5. And then divide that whole thing by 2. And I get about 3.477. right, take a look at D. Your first reaction might be, wow, that looks a lot more complicated. But actually, with one simple step, it's going to look just about like the last one we did. We are multiplying those exponentials. Remember when you multiply exponentials? What do you do to the powers? You add them, right? So I'm going to say this is an exponential base 3, and it's still base 3. But I'm just going to add the x minus 1 plus the x plus 5. Again, we only add the exponents, we don't change the base. So that's 3 to the 2x plus 4 equals 243. All right, exponential is now isolated. To get rid of an exponential base 3, I would use a log base 3. And of course, I have to do it on both sides. All right, I got those inverse functions going on there. And that's going to leave me 2x plus 4. And for right now, well, actually, you know what? I think that one actually comes out evenly. I think 3 to the 5th power is 243. Let's check this one out. I'm predicting we're going to get 5. The log base 3 of 243. Yep. So because that log came out evenly, it's just 5. All right, this one makes this one relatively easy to finish up. We'll subtract the 4, so 2x equals 1, and that means x will be 1/2. All right, the next couple of examples have got the exponentials base e in them. And I'm going to work them exactly the same way, just remembering that the inverse function for a log base e is the natural log. So, got to isolate my exponential. This right here would be the exponential. So I got to subtract the 5. 8 e to the 3x minus 1 equals 28. And then divide by the 8. So e to the 3x minus 1 equals, let's see, that would be, well, let's just divide it out. Uh, 3.5. All right, I need to get rid of the exponential base e. The inverse function is the natural log. So I take the natural log of e to the 3x minus 1, and on the other side, the natural log of 3.5. There are those inverse functions again. That just leaves us 3x minus 1 equals the natural log of 3.5. If I'd like to keep an exact answer, I would have to add the 1. Again, remember that 3.5 is in the argument. It cannot be combined with the 1. Really can't get it out of the log at this point. So let's see, to get x by itself, then I just need to divide by 3. So that's my exact answer right there. And if I want a decimal approximation, I'll just do this one in the calculator. I would have the natural log of 3.5, add 1, parentheses, all of that divided by 3. So about 0.751 if I'm rounding to 3 decimal places. All right, let's do one more exponential equation with a base of e. This one's a little bit different because you've got two e to the x's in the equation. What we want to do is combine them. We want to get them together. So what I'll do is I'll subtract e to the x from both sides. And remember, that's really a 1 e to the x. So 3 e to the x minus 1 e to the x would be 2 e to the x. Then I've got a minus 12 equals 44. I want to get the e to the x by itself, right? This is my exponential this time is relatively simple. It's just e to the x. So to get that by itself, I'm going to add 12. 2 e to the x equals 56. And divide by 2. E to the x equals 28. All right, my exponential is by itself, so I want to take the natural log of both sides. Inverse functions. So my exact answer is just x equals the natural log of 28. And of course I can also do that on either the calculator or Desmos. Natural log of 28 is about 3.332.